Hi, Assalamualaikum. With me, Puan Siti Aminah. We will learn chemistry lecture about a topic thermochemistry chapter 2. Let's go. Okay, in 2.1, concept of enthalpy, there is three learning outcomes that we will learn. The first is we can explain after this about endothermic and exothermic reactions using complete energy profile. And second is state standard condition or reaction and define term of enthalpy and standard enthalpy. What the difference between enthalpy and standard enthalpy? And the third one is define and write 6 selected thermochemical equations. So what is thermochemistry about? Okay, thermochemistry is a study of heat change. Okay, perubahan tenaga in chemical reactions. Almost all chemical reaction absorb, okay, or we can call produce, release energy in form of heat. There is two types of chemical reactions. The first one is exothermic. Okay. In exothermic, surrounding is a little bit higher the temperature compared to system, meaning that in exothermic system will release heat to surrounding. So it make the temperature of system will decrease. In the same time, the temperature of surrounding will increase. Okay. What about endothermic? Endothermic is a process which is system absorbing heat from surrounding. So it's made the system will increase its temperature and in the same time surrounding will lower its temperature. Okay. So there is a few important terms that you have to know. The first one is heat is energy transferred. Okay, transferred, dipindahkan between two bodies of different temperature. If we got two objects with different temperature, 200 degree and 100 degree, so these two objects will lastly have an equal temperature because the object that have a higher temperature will release heat to the object that have a lower temperature. So what is system? System is any specific part of the universe. Good. System is an object. Either it releases or it absorbs heat. It's the main point of the reactions. Okay. And the surrounding is everything that lies outside the system. Okay. So the main character here is the system. And the supporting system and the supporting way ataupun the supporting object we call surrounding. Apa sahaja sekitar objek adalah surrounding. Maybe surrounding ada two things or three things or maybe one part only. Okay, that support the system. And the most important is the heat, orang kata tenaga heat is terabadi. Okay, meaning that whatever heat released will be equal to the heat absorbed. Okay, this is the example. If you see here, we've got an orange solutions that contain in the past we call as a system, and this system, what everything lies outside the system is called surrounding, including the container, the flask, the laboratory, and whatsoever outside the system is we call surrounding. Okay, about a system. Okay, there is three types of system. The first one is open system. What is open system? Open system is a system that can exchange mass and energy with its surrounding. Meaning that, the system, example, we have a cup of coffee. Okay, This is an example of open system. Okay. So by time goes by, the temperature will be lowered and also the mass of the coffee will be decreases. So this is an example for an open system. Okay, what is a closed system? Closed system is a system that allows the exchange of energy with its surrounding. So if this coffee cup, okay, have a lid, penutup, this is example of what we call isolated system. So in closed system, example of closed system, okay, when we have a coffee cup and we close it with a lid, okay, by the time goes by, the temperature of the coffee will be lowered, but the mass is remain because we have a lid that block all the mass of coffee to move out. Okay, so this is closed system. So what about isolated system? Okay, and the last system. Isolated system is a system that does not allow any change, either mass, okay, either mass or energy in terms of heat with its surrounding. For example, is thermos, okay, thermoflask, okay, and the energy, the heat is remain, same goes with the mass, okay. Ini adalah example for isolated systems. So, we go to the next issue, which is exothermic reaction. What is exo? Maybe you familiar with word exo. You have already learned in your secondary school. Okay, let's recall what we have learned. Enthalpy of reactant. In exothermic, enthalpy of reactant harbor, okay, energy of reactant, what that we call enthalpy, is always higher than a product. So, in order the reactant want to convert to be a product, so some of energy of that reactants have to release to surrounding so that the product will be formed. When the energy is released, the enthalpy is negative. Negative is classified as energy release. Right? This is what we call energy profile diagram for exothermic process. Consider the following reactions. We have A plus B as our reactant in a gaseous state and will form a C product also in a gaseous state, and the enthalpy change is negative. It shows that this reaction is exothermic. So that A and B here is reactant has a little bit higher enthalpy compared to the product. So in order reactants, enthalpy of reactants, okay, to reach the enthalpy of product, some of the heat in reactant must release. Okay, so that energy is released from reactant to the surrounding. So this is example energy profile diagram for exothermic process. Y-axis is enthalpy, or sometimes we can replace with heat, okay, and the x-axis is reaction pathway or reaction progress. This A show enthalpy of reactant. This B show the enthalpy of product, and the difference is the enthalpy of reaction. Let's go to endothermic reactions. What is about endothermic reaction? So in endothermic reaction, the enthalpy of reactant is a little bit lower than enthalpy of product. Okay, so the delta H here is positive. In order reactant, enthalpy of reactant want to reach enthalpy of product, so reactant has to absorb heat from the surrounding. So this is example of energy profile diagram, endothermic reactions. What you can see here, we have A and B as our reactant and want to form C as our product. The enthalpy show is positive, so it is recognized as endothermic process. Reactants have lower enthalpy compared to the product. So this A shows us that it is enthalpy of product, B is enthalpy of reactant. So A minus B is delta H. It shows that this is enthalpy that the reactant has to absorb in order to form a product. Okay. There is some terms that you have to know and to remember. The first one is energy. What is energy? Energy is ability to do work. In SI unit, energy is kilojoule meter square per S negative 2, or easily can be known as joule. Non-standard unit for energy is calorie. Okay, and calorie known as 4.184 joule. 1 calorie equal to 4.18 joule. And what's about enthalpy? Okay, the enthalpy change associated with a chemical reaction. Okay, what the difference between standard enthalpy and enthalpy of reactions? So enthalpy of reactions equal to enthalpy of product minus enthalpy of reactant. Okay, so the enthalpy change associated with a chemical reaction in difference between enthalpy of product and the enthalpy of reactant. Okay. This is enthalpy of reactions. But what is standard enthalpy? The word here is the enthalpy change, delta H, for any particular reactions that occur in 298 Kelvin and 180 atm, that we call standard state. So if you mention whatever enthalpy, whatever reactions, okay, that occur during these two conditions, pressure and temperature, we call as standard enthalpy. And the symbol here, delta H, there is now. Okay, ada kosong, ada now symbol at delta H. So we know this as a standard. This now stands for standard. And the reactions must occur in 298 Kelvin and 180 atm. So that is the difference between standard enthalpy and enthalpy itself. There is 6 enthalpy that you have to know how to write the enthalpy. Okay, the first one is formation, combustion, the third one atomization, fourth one neutralization, hydration, and the last one is solutions. Let's go one by one. Okay, enthalpy of formation. So enthalpy of formation we call as delta. Okay, the difference. H is enthalpy. F stands for formation, so we use a symbol subscribe F. F stands for formation. So what is definition for enthalpy of formations? So the change of heat. When we mention the change of heat, meaning it can be endo and it can be exo. Okay? The change of heat when 1 mole of a compound is formed from its element at their most stable state at stated conditions. And this stated condition may be 100 degree or 180 atm. But when you're talking about the standard enthalpy formation standard we have now, you must mention at 298 Kelvin and 180 atm. If we are talking about standard enthalpy. Alright? So at stated condition, it depends on the what kind of question you are discussing, what the data of temperature and pressure of the reactions occur. Alright, so every word in this definition show us how to write enthalpy of formation in correct way. That's why you have to remember and to understand before you draw or you write your thermochemical equation of enthalpy formations. So here we've got hydrogen gas react with half of oxygen gas forming H2O. So this is example of enthalpy formation of water because it says that a compound is formed. Okay, the product, a compound is formed, meaning that water is formed. So this is enthalpy of water. From what? From its element. Water, element from water is hydrogen and oxygen. Okay, there is no other element. You can see here. So hydrogen, element of hydrogen is gases and element of oxygen is O2 gases. So you have to put half here in order to balance with 1 mole of product. Okay, because enthalpy of formation, the product must be 1 mole. That's why there are this color 1 mole with a purple color. Okay, so 1 mole here is a product because this is enthalpy formation of product. Okay, so the enthalpy formation for each 1 mole of water is negative 286 kilojoule per mole. What it means is every 1 mole of water being formed from each element, the reactants will release about negative 286 kilojoule. Right? So the one more thing tips for enthalpy formation stated here is the standard enthalpy formation of any element in the most stable state is 0. What is element? Element is oxygen, element is chlorine, element is bromine. Okay, so this kind of element is already exists in our world. So the enthalpy is 0. Okay, it already being formed without any reactions. That's why the enthalpy is 0. You don't have to prepare it. It's already there. Okay, that's why enthalpy for element is 0. But the enthalpy is what for water, we have a value because water is not element. Water is a compound. Alright? So this example for standard enthalpy formation. So we have now here the change of heat when 1 mole of compound is formed from its element at the most stable state, 25 degree and 1 atm is mentioned the temperature and pressure because we are talking about the standard enthalpy. So the temperature and pressure must be mentioned at stated value. Alright. For example here, water. And the second example is enthalpy for carbon dioxide, CO2. The enthalpy of carbon dioxide to form 1 mole of carbon dioxide, okay, carbon and oxygen is the element for carbon dioxide. So carbon is solid, oxygen is gases, O2 is gases, exists as gases. So these two things must combine, balance the equation. In the same time, make sure the carbon dioxide is 1 mole, okay, and the enthalpy here is negative 393.5 kilojoule per mole, meaning that, reactant carbon and oxygen have to release about 393.5 kilojoule heat in order to form 1 mole of carbon dioxide. Okay, so here example, everything you have to know to form any compound, it must come from its natural element. Okay, and the compound must be 1 mole because the stated in the definition enthalpy formation. Okay, for check hydrogen plus water to form 2H2O, this is not enthalpy formation because the compound, okay, the product of water is not 1 mole, it is 2 mole. So this is not enthalpy for formation. Okay, the enthalpy for formation must be 1 mole. If you want to know what is enthalpy for formation, you have to divide with 2, because here the product is 2 mole. So negative 572 you have to divide by the number of 2 in order to get 1 mole. Okay, next is enthalpy of combustion. Combustion is pembakaran. Okay, so we have to use the word here is heat release. Okay, combustion is always exothermic. There is no heat change. It cannot be endothermic. So that's why it uses the term of heat release. So the heat release when 1 mole of substance here is show that the compound that we burn. Okay, 1 mole of substance that we burn completely in excess oxygen. So 1 mole here is no longer the product, but is reactants. Okay, reactant that being burned. So here is enthalpy formation for carbon being burned in excess oxygen to form carbon dioxide. Okay, make sure the reactant carbon is 1 mole. So from here we know that carbon release, okay, carbon release about negative 393 kilojoule. Okay, for each 1 mole being burned. If we are talking about enthalpy, standard enthalpy for combustion, there is a null here. Okay, the heat release same when 1 mole of substance. Okay, same with the above statement, is burned completely in excess oxygen at 298 Kelvin and 180 M. So the standard state you have to mention temperature and pressure. Okay. This is the example of combustion, carbon and methane. Methane burn, 1 mole of methane burn in excess oxygen to form carbon dioxide and water. Okay, there is a tip here. Every hydrocarbon that burns in excess oxygen will form 2 things, which is asap dan air, yaitu carbon dioxide and water. Okay, whatever hydrocarbon, carbon hidrogen mana pun terbakar with oxygens will form these 2 things, but you have to mix it balance. Okay, okay, remain the 1 mole for the compound that being burned. Okay, what about enthalpy of atomization? Enthalpy of atomization, the symbol is delta HA. Okay, delta HA. A stands for atomization. The heat absorbed, because atomized is always absorbing heat. Okay, when 1 mole of gaseous atom being formed from its element, and delta HA is always positive, as I told you, because it only involves breaking the bond. Okay, to form an atom. Atom is the simplest particles. Okay, so to form an atom, you must break the bigger particles. So breaking any bond require heat. That's why enthalpy of atomization always endothermic. Okay, for example here, we've got sodium in a solid phase, because sodium in a natural element 25 degree 180 M, sodium exists as a solid. Okay, it is no longer we cannot call it as an atom because it in a solid phase. Okay, atom must be in gaseous phase. So in order sodium solid to form a sodium atom, so this solid particle must be break. Okay, and the particle must be tear apart, okay, the distance, so that the solid particles that close apart will be have a distance between the particles, so that it exists as a gas. So enthalpy atomization for sodium solid to form a sodium gas, which what we call atom of sodium, the energy required is about 109 kilojoule for that the sodium solid to absorb in order to break the bond. Same goes with chlorine. Okay, chlorine atom is Cl gas, but chlorine itself exists as Cl2. Okay, chlorine at 25 degree 180 NaMCl to exist as molecule. So in order chlorine to form a chlorine atom, chlorine molecule to form chlorine atom, this molecule have to absorb heat about 121 so that the chlorine molecule will be stirred and will be split to be chlorine atom, right? Jadi kamu boleh balancekan yang lain but bukan pada chlorine atom because this is enthalpy for atomization. So the atom must be 1 mole. Okay? If you have 2 mole of chlorine, meaning that 1 to 1 must be times by 2. Kalau you have 2 mole of chlorine atom. So for example, if we have these equations below, so we are no longer can call it as an enthalpy atomization because this atom is no 1 mole of atom. It is 2 mole of atom. It's just delta H. You cannot put an A here. Okay. So if you want to calculate what is enthalpy atomization, you have to divide by 2 because this is 2 for 2 mole atom. If for 1 mole atom, you have to divide 2 for 2 with 2. Okay, and to be 1 to 1 kilojoule per mole. Okay, let's move to be to enthalpy neutralization. Neutralization commonly we know as when an acid reacts with base and these two things mix and it neutralizes to be maybe salt and water. Okay, so what is enthalpy neutralizations? And we have to put N here, the small n after delta H, so that we know N here it shows the acronym for neutralization. So what is enthalpy neutralization definition? Is the heat release. Okay, heat release. It shows that neutralization always exothermic. When 1 mole of water is formed from a neutralization of acid and base. For example, we use a common acid and base in lab. Okay, hydrochloric acid react with sodium hydroxide to form sodium chloride and water. Okay, so the value of delta Hn is negative 58 kilojoule per mole. The H2O here is shows that enthalpy of neutralization. For each 1 mole of water formed, it release the reaction of hydrochloric and sodium hydroxide will release about will release 58 kilojoule of heat. Okay, in each mole of water being formed. Okay, the most important here to remain 1 mole is to the water. Not for the acid, either base or product sodium chloride, but the neutralization you have to focus on water being formed. The stoichiometry must be 1 for the water. Alright. Enthalpy of hydrations. Sorry, yeah. Enthalpy of hydration, the symbol is HYD. HYD stands for hydration. So the heat change. Because the enthalpy hydration can be endo, can be exo. It is for 1 mole of gaseous ion hydrated in water. Okay, so we have gaseous ion and we put in water, so it will form a gaseous aqueous. An aqueous ion. For example, the equations that you can see here, we have sodium plus gas. So we have a gaseous ion, 1 mole here, 1 mole sodium gases, okay, and it will form Na plus aqueous after we mix with hydrated in water. So each 1 mole of sodium plus gas hydrated in water, it release about negative 4 negative it release 406 kilojoule of heat for each 1 mole of sodium plus gas hydrated. Same goes with chlorine gases hydrated, meaning that setiap each of particle ion gases hydrated, it will form ion but in aqueous phase. So the difference here is only phase from gaseous ion to form aqueous ion after hydrated with water. And the 1 mole is stand for the reactant. Okay, so that's why very important for you to know the definition very well for each of enthalpy, so that the thermochemical equation you can write in correct way. After you write the chemical equations, put aside, okay, you must write beside of the chemical reaction with delta H. So we call it one set of chemical equation with delta H as thermochemical equation. So what is thermochemical equation? Adalah enthalpy beserta dengan plus with chemical equation. What is enthalpy solution? Enthalpy solution is the heat change. So this example meaning that solution can be exo or sometimes it can be endo. So each 1 mole of substance when dissolved in water, okay, this is what we call enthalpy of solution. For example, we have 1 mole of KCl solid, garam, garam, salt of KCl, 1 mole. After it dissolved in water, it will split to be ion in aqueous solution. So each mole of 1 KCl solid dissolved in water, we call as enthalpy solutions, and it will absorb heat about 619 kilojoule in order to form K plus aqueous and Cl minus aqueous. So this example of enthalpy solution. If you see the enthalpy solution positive, meaning that this salt, okay, this salt is difficult to dissolve in water. Okay, it is insoluble salt, so it requires heat to dissolve so that it can dissolve in water very well. So KCl is example that insoluble salt. Alright, thermochemical equation. In thermochemical equation, it is chemical equation which include, you must include phase label and you must include the delta H, okay, the heat of reaction. So, example, we have enthalpy of combustion here. We have CH4 gas react with 2O2 gas. So here we have phase, and then to form carbon dioxide and water. Besides this chemical equation, okay, we put delta H so that this set of chemical change we call as thermochemical equation. Without delta H is only chemical equation, but with delta H is known as thermochemical equation. For example, we have example of H2O solid, which an ice, okay, after melt to form H2O liquid, 1 mole of solid melt, it absorb heat from the surrounding about 6.01 kilojoule. Okay, so this is example for thermochemical equation because we have chemical equations and plus we have delta H include in this chemical equation. So these two things when combined we call as thermochemical equations. Okay, when a chemical equation is being reversed, okay, kita terbalikkan. The chemical equation being reversed, the value of delta H, okay, the magnitude of delta H is remain, but the sign of delta H is changed. For example, okay, we have this equation, delta H is negative 890.4 kilojoule, but if you reverse the equation, the product to be reactant and the reactant convert to the product. Okay, and the 890.4 kilojoule is remain, but the sign of negative change to be positive. Okay, so whenever you change, you reverse the equation, the sign of enthalpy also being changed. Okay. Okay. Thermochemical equation, for example, here, when 1 mole of liquid water is formed from 1 mole of ice at 0 degree, the enthalpy change is 6.01 kilojoule. For reverse, negative 6.01. Okay, now the next subtopic is 2.2, which is calorimeter. We already passed our 2.1. Okay, this is 2.2. What you should know in this 2.2 is, in this lecture, you will learn a lot of things in your tutorial. But in this lecture of 2.2, you only have to know the definitions of heat capacity and specific heat capacity. Okay, and this reaction you already make it in experiment 1 this way. Okay, so what is calorimetry? Calorimetry is a method in laboratory to measure the heat change of a reaction. Okay, and the apparatus that used in calorimetry we call as calorimeter. And there is two types of calorimeter. One is simple calorimeter in a constant pressure, and a big complex of calorimeter we call bomb calorimeter. In this bomb calorimeter, the constant thing is a volume. What is simple calorimeter? Simple calorimeter is like this one. We use styrofoam cup, and we have a thermometer instead of stirrer. So all the reactions occur in the styrofoam cup. When heat released by the reaction is absorbed by the solution and the calorimeter. This is simple calorimeter. So whatever reaction, whatever the system is occur in the styrofoam cup. So the things that absorb the heat or release the heat, okay, whatever the surrounding adalah we call the solution in the styrofoam cup, as well as the calorimeter will be the surrounding of the system. Okay. So the outer styrofoam cup insulate. Insulate maksudnya dia kedap haba Okay. The reaction mixture from the surrounding, it is assumed that no heat is lost to the surrounding. There is no heat loss to the surrounding because we use a styrofoam cup. So this is example of bomb calorimeter. Okay, when the reaction is set up, heat is liberated and absorbed by the bomb and the water inside the bomb calorimeter. Okay, so in this bomb calorimeter, the volume is constant. Okay, so the important terms in calorimeter, one is specific heat capacity with the symbol small c, okay, and the second is heat capacity with the symbol capital of C, okay. What is specific heat? Specific heat capacity, small c, okay, the symbol. So specific heat capacity of a substance is the amount of heat required to raise the temperature for 1 gram. The mention there is 1 gram. For each 1 gram, to increase 1 degree Celsius, how many joule, how many heat is required? So this is specific heat capacity. Okay, mention 1 gram. For each 1 degree to increase, how many joule is required for that thing, that object. Okay, but for heat capacity, it just defined as amount of heat required to raise a temperature for 1 degree, okay, for any quantity of a substance. Doesn't mention how many gram, but for specific heat capacity for 1 gram of a substance. That the different things between specific heat capacity and heat capacity, only at the gram. Okay. Okay, as I told you earlier, Haber adalah terabadi, meaning that heat released by the substance equal heat absorbed by calorimeter. Okay. The main point there is whatever heat released must be equal with the heat absorbed. If released 2 joule, must absorb 2 joule. If absorbed 3 joule, must release 3 joule. Okay. So the formula for heat, the symbol for heat is Q. Okay. So Q equal to M times M is mass times C. C is specific heat capacity. Delta T is the change of temperature. Maybe in Kelvin or can be Celsius because it only delta T. Okay, doesn't important either in must be in Kelvin or Celsius. Right? Or you can use either than MC delta T, you can use C delta T. But C delta T is C is heat capacity time with delta T. If the question gives you C, capital of C, this is the formula to calculate Q reactions. Okay? How to calculate you will learn deeply in your tutorial sessions. And the unit specific heat capacity is joule per gram per Celsius. Meanwhile, the heat capacity unit is joule per Celsius. Okay, Hess law 2.3. What you have to know about Hess law is definition of Hess law. What is Hess law means? Okay, Hess law states that when a reactant are converted to product, the change of enthalpy is the same whether the reactions take place in one step or a series of steps. Right? So the enthalpy change depends only on the nature of reactant and product, and it is independent on the route taken. For example, we have A to form a B, from a reactant A to form a product of B. So the enthalpy involved is delta H1. Right? There is another way to form a B, okay, which is A partially form C as a transition state, and this C transition state will form B at the end of the reactions. So when A to form a C, delta H2 is included, is take place when A to change a C, and when C want to be a product B, final product, delta H3 is take place, is included in these reactions. So from here we know that delta H1 is equal with the combination of the two routes A to form a C and C to form a B. Delta H1 equal to delta H2 plus delta H3. This is what Hess law told us, meaning that whatever the heat change is only depend on the reaction. Okay, it's no depend to the series of a reaction. And the last one in this lecture, 2.4, it is about Born-Haber cycle. There is two learning outcomes that you have to master in this lecture. The first one, you have to know how to define lattice energy and electron affinity. And the second one, you have to know how to explain the effect of magnitude of lattice energy toward ionic charge and ionic radii. So what is ionization energy? Energy required to remove 1 mole of electron from 1 mole of atom in gaseous state. For example, we have magnesium gas. Okay, this is atom magnesium. Okay, and it will form ion magnesium Mg plus gas after being removed. 1 mole after being removed and valence electron, it will form Mg plus. So this is first ionization energy for magnesium atom. And the ionization energy for each 1 mole of magnesium atom is 740 kilojoule of heat must absorb. Okay, so that the electron can be removed. The second time electron want to be removed, okay, so it more difficult because the size of ion becomes smaller from its previous atom. All right. So when the size becomes smaller, it's required a lot of energy compared to previous one. All right. So the second time electron want to be removed from Mg plus because it already changed to be Mg plus ion. Okay. So this is what we call second ionization energy. And the second IE is 1400 kilojoule for Mg plus gas to release the second electron from its valence. What about electron affinity? Electron affinity is vice versa to ionization energy. If ionization energy want to form a positive ion, electron affinity want to form a negative ion. So what is electron affinity? It's about the heat change because it can be positive and negative. Okay, it can be endo and it can be iso. But ionization energy is always endo. It's always positive. Okay. So electron affinity is heat change. When 1 mole of gaseous atom gain, the word here is gain, okay, receive 1 mole of electron to form 1 mole of gaseous ion, 1 mole of negative gaseous ion. Okay, for example, here we have oxygen gas. After receive 1 electron and put in valence shell, and put in valence shell, oxygen atom, okay, turn atau change to be oxygen negative gas, okay, O minus gas. So this is electron affinity because the electron being added to the valence. So each 1 mole of gas when receive 1 mole of electron, it release negative 142 kilojoule. So this is the first electron affinity for oxygen. The second electron affinity is after the second time the electron must be added to already O negative ion. The second time. Okay. So O negative to become O2 negative. This is the second electron affinity. So it is a bit difficult because you already in a charge negative. Then you want to the ion want to receive another negative. So the what we call the energy negative charge and the electron will repel. In order to force the electron include, okay, to put in our valence, so some energy must be absorbed. Okay, that's why the first EA always negative, but the second EA is changed to be positive because this process, the second process is harder compared with the first EA. So lattice energy. Lattice energy is the heat change when 1 mole of solid, which is ionic compound, is formed from its constituent gaseous ion. We call as lattice formation. For example, okay, we have sodium gas plus chlorine minus gas, sodium plus gas plus chlorine minus gas to form an NaCl solid. So when 1 mole of solid ionic compound is formed, we call it as a lattice energy formation because 1 mole of solid lattice being formed. So each 1 mole sodium chloride solid is formed, there is 771 kilojoule is released from its reactant. Okay. So the lattice energy change are large and the value negative for the formation, meaning that if the lattice formation is always negative, but the lattice dissociation, we can what we call change the sign here, meaning that sodium chloride pula pecah, okay, dissociate to be ion. When the sodium chloride dissociate to be ion, the sign of delta H also being changed to be positive 771 kilojoule. But that things we call lattice dissociation. And this equation that I show you in the slide is lattice formation. So this is what we call lattice dissociation. The sign has been changed because from sodium chloride dissociate to be is ion. Okay, so it must involve a breaking a bond. Okay, now the magnitude of lattice, okay, tenaga kekisi, is increased as the ionic charge increase. Okay, for example, kalau lah if the sodium chloride, sodium is plus, chloride is negative, plus 1, negative 1. If the charge increase, the magnitude 771 should be increased. Okay, so the magnitude is depend on the charge of the solid lattice. And the second factor of magnitude of delta H is also about to the ionic radii. If the ionic radii decrease, the lattice energy increase. So we know that the lattice energy is directly proportional with ionic charge but inversely proportional with ionic radii. Right? So the energy required to completely separate 1 mole of solid ionic compound into gaseous ion we call as enthalpy lattice dissociation. Okay, for example, there is strong attraction between small ion and highly charged so that the delta H is more negative. Delta H for magnesium oxide is more negative. Magnesium is 2 plus, oxygen is 2 minus. Compare with Na is plus, oxygen is negative 2. So if you compare the charge, magnesium oxide is higher charge compared to sodium oxide. Therefore, lattice energy magnesium oxide is higher than lattice energy sodium oxide. The first thing you have to compare is look at the charge. If the charge is the same, then you can see the radii. Okay, so the last one, what I can share to you is, common say chemistry is study of matter, right? But it actually the best to be seen is study of change, like this change of enthalpy in thermochemical topic. Same for us, human being. We must change to be better, no matter how good or bad we are in previously. So that's all for today. Assalamualaikum.